Welcome back to another class. Hi to all of you, and today's topic is very interesting because we'll learn about different electrophoretic technique, that is PFGE and capillary gel electrophoresis. Believe me, it's very interesting and very exciting topic. The reason being that you will see the beauty of gel electrophoresis. PFGE means Pulse Field Gel Electrophoresis, a very bright technique that leads to separation of DNA of more than 28 kilobase pairs. Sorry, more than around 1 MB of DNA to 10 MB of DNA can be separated here. Now see, the gel electrophoresis or polyacrylamide gel electrophoresis has a limitation for DNA separation. The limitation is that the size of the DNA fragment that it can accommodate. The gel electrophoresis, we know that the pore size is very large, like 3% gel also has large pore size. But the problem with the gel electrophoresis is that it is in the one dimensional. It is only in the one dimension, and if we want to separate chromosome, if we want to separate larger fragments of the DNA, then the DNA doesn't separate properly, or it is similar to taking a hose pipe out of a garden of bushes. So that's how the DNA travels into the gel. Okay, so solve that problem, a technique known as pulse field gel electrophoresis. I'll come to capillary electrophoresis also, but before that we should discuss pulse field gel electrophoresis. Okay, so yes, pulse field gel electrophoresis, what we do is the gel is normal. For example, this gel we have got, okay, and we use around 1% gel only. Wait a second, we use 1% gel. Why? Because as I told you that pulse field gel electrophoresis is used to separate larger chunks of the DNA, larger DNA, around 1 MB to 10 MB of the DNA. MB means mega base pairs. Okay, so now you will load the DNA here, and the beauty lies in the fact that in normal gel electrophoresis, what we do, we add a negative electrode, that is cathode here, and anode here. Okay, but in pulse field, as you can understand, pulse is getting, and the field is changing. That means here initially the field was in this direction. So now what we do, we put additional electrodes at 60 degrees. At 60 degrees, I'll just make a temporary line and I'll just remove it afterwards. So at 60 degrees, we put again electrodes here, and the similar will go here. Okay, and I'll just remove this. Similarly, another at 60 degree. So at 60 degrees here also we put the electrodes, and similar to this area we put the electrodes here. So two electrodes at 120 degrees and one electrode at in the middle, that is normal gel electrophoresis. So I'll remove all the sections now. Yes, so this is how a pulse field gel electrophoretic techniques looks like. Now see, the problem you see, when we were able to when we tried to run long amount of long DNA like this on normal gel electrophoresis, the problem which we face is the pore size first, because we cannot induce, we use 0.6 to 1% gel, and this is a quite large pore size, but still large DNA is not able to run properly in this pore size. Large DNA is able to just run like this. So this is the large DNA that has been compressed, and that's why the DNA cannot properly form a band. But with pulse field gel electrophoresis, what we do, we give the DNA the mobility to move here and there, here and there, here and there, like it's dancing, like this. So what happens? First, the DNA will move like this. The first. In the second pulse, the DNA move like this. In the third pulse, the DNA will again move like this. Then again it will move like this. Then again it will move like this. Move like this. Move like this. Okay. So you see you see the migration pattern. First it was straight, then for a short amount of time voltage per meter was applied, and it should be this we have to keep in mind that the frequency, the time duration of the pulse is very important. For larger chunks of the DNA, if you increase the time of the duration of this time for which the pulse you are providing in any of the direction, it will lead to better resolution. For larger DNA, better resolution if you increase the time period. So this is, I am telling you the factors on which it depends. For a smaller chunk, relatively smaller chunk, so large time. For smaller chunks, small time intervals should be decided. Small time intervals for what? Small time intervals for these pulses. It will give you better resolution. Okay, so yes, for a large chunk of DNA, larger time intervals. For smaller chunks, smaller time intervals. So the DNA doesn't move straight, but the DNA moves like this, then for a short amount of time like this, then for a short amount of like this, and this should be equal. This and this should be equal, and finally for a short amount of time this should also be equal. Then goes this, then like this, then like this. So except we actually, what is happening in a normal gel, the time duration is not proper. The time duration is very less for the DNA to move in a single area. For example, the area is, the length is this much only, this much only. But if you see for pulse field, the length has increased. The length has increased, this and this has increased. Again, this and this has increased. So DNA is not only moving in the straight, but it is also moving in the diagonal form. And alternatively, this is applied. For example, the first pulse is this, then the second pulse is this, then the third pulse is this. So the pulse is something like this, like this, like this. Okay, in all directions. So this is known as pulse field gel electrophoresis, and the apparatus is something like that. The electrodes are placed like this. Okay, got the point. So 3 different electric fields we are getting here, and remember the angle, it is 120 degrees, 60 degrees with respect to the straight line and 120 degrees between the 2 diagonal sides. Okay, and how this helps is that the DNA gets more and more lengthwise time, and again the DNA is getting, you can say,